Well, Jim Wilkinson has been discussing the algorithmic background of the EISPACK matrix eigenvalue codes. These, of course, algol programs implementing these codes are available in the Wilkinson and Reinsch handbook. As these codes have been developed, the work here, simultaneously with the development of the algol codes here, the group here at Argonne has been working on the Fortran. And for the benefit of the TV audience in particular, I should mention that the people that have been involved in the Fortran here, Virginia Cleve did much of the original translation from algol to Fortran, and Bert Garbo, Brian Smith, and Jim Boyle have been involved here more recently with the refinement and checkout of the code. I personally have not written one line of the codes I'm going to talk about. What I want to do is take two of the most important codes, namely TRED2 and TQL2, and translate the algorithmic formulation, the formulation of the algorithms in terms of the matrix notation that Wilkinson's been using into Fortran to the point where we can go through and understand line by line the Fortran programs, or at least most of them, most of the lines. Now these are two of the simpler programs, but they illustrate many of the points. They're two of the simpler, but they're two of the more important, and they illustrate many of the points that occur in some of the longer programs. These, of course, find all the eigenvalues and all the eigenvectors of a real symmetric matrix. We could take little simpler programs, TRED1 and TQL1, and avoid the eigenvector calculation, but there's a couple points I want to talk about, a couple points about the eigenvectors that I want to talk about. So what I'll do is describe the algorithms that are involved in these two programs using somewhat the notation that's actually used in the Fortran code, and then we'll put the actual Fortran code up on the screen and go through it line by line. Okay, the first one is TRED2. TRED2 takes a real symmetric n by n matrix A and transforms it into a tridiagonal matrix like this, a diagonal, a super to subdiagonal. It remains symmetric, so the super and subdiagonal are the same, and the notation is D1, D2, down through Dn is the diagonal, and then, well, there's great international debate, transatlantic and transcontinental debate about what the super and subdiagonal should be called, and we sort of vacillate between calling them E2 through En and E1 through En minus 1. In fact, TRED1 uses, the TRED uses one set of E's and TQL uses the other set of E's, and there has to be a slight transformation when you go from one to the other. So we're going to discuss this first. As Jim pointed out, there's a great deal of concern with graded matrices, whose elements vary in a fairly regular way over wide magnitudes, and it's his experience that the elements tend to grow as you go down the matrix. And for this reason, it was decided to do householder backwards. So you start at the bottom of the matrix and work up, rather than start at the top and work down. So let's try and describe it in that terms. I'll take a 5 by 5 matrix of x's. Jim can put these up much faster on the board than I can. Now we're working with a symmetric matrix, and so I actually didn't need to put up half those x's. In fact, we're never going to touch that part of the matrix. We'll never look at what's there, and we'll never put anything in there. Right? So if you catch me fiddling with the top half of the matrix, you get to yell at me. Okay? So all the information is stored on the diagonal in the lower half. And in fact, we're even going to preserve the diagonal. So the whole matrix will be preserved. All the information of the matrix will be preserved. But in order to preserve the diagonal, we're going to have to transfer it bit by bit into an intermediate vector and then come back into here. All right, now our first job with the householder tridiagonalization is to wipe out these elements except for the diagonal and the subdiagonal. And because of the graded matrices, we're going to start out down here at the bottom, and we're going to wipe out these three elements first. So let me give those, put in the names of those elements. Here's AN1, AN2, AN3, AN4, and AN5. And now we're going to try and annihilate, we're now going to annihilate the first three of those with a householder transformation. And so we define A to be the vector AN1, AN2, AN3, AN4. Just that vector of length 4. Well, let's put a 0 here. Okay, so we'll get a matrix of the right size. That is, we're going to leave the diagonal element alone and work with those first 4 elements and annihilate the first 3 of them. Now, the first part of the process is to compute the length of that vector. And in the Algol, and hence in the Fortran code, that's called G, for I have no idea why. And G is defined to be the sign minus the sign of AN4 times the length of A. Right? So the first computation we're going to see is compute the sum of the squares of those 4 elements. Take the square root to get the length. That's going to be the only square root involved in the computation. And then take plus or minus that square root according to the sign of this number. And that's not quite the first computation we're going to see. There's some scaling that goes on before that, and I'm going to tend to skip over the details of the scaling, but let me mention at least the need for it. Say all these elements were kind of small. Well, let's say that, well, quite small. Say they were all on the order of 10 to the minus 40th. 1 times 10 to the 40th, 2 times 10 to the minus 40th, and so on the 360. Now, in computing the sum of the squares of those numbers, we would then get 10 to the minus 80th, which would underflow and be 0. But then the number we actually want to get out is back down to 10 to the minus 40th. Right? Now, it's not so unlikely that something like this is going to happen. If we have a matrix with multiple eigenvalues, then we are going to have to end up, well, in principle with exact arithmetic, we'll end up with some 0 subdiagonal elements in the tridiagonal matrix. And this number is going to be an element of the tridiagonal matrix. So if we have a matrix with multiple eigenvalues, and if we did exact computation, then some of these G's are going to be exact 0. And so it is entirely conceivable that we will get very small numbers. So the way this is handled in Fortran is different than in Algol. The Algol program required a parameter called tall, which was actually in the calling sequence, the Algol procedure, which had something to do with the underflow level of your particular machine. We found that that was a great nuisance for users. And so instead, in the Fortran program, this column is gone over once, and the sum of the absolute values of the elements is calculated. That won't underflow. then that sum is used as a scale factor, since we're really only interested in the ratios of the sizes of these elements. So there's some scaling that goes on, but we'll see that in the program, but let's forget about it. Let's not worry about actually the details of how it's carried out. So we compute the length of that vector, and then we define a new vector, which is the same as the old vector, an1, an2, an3, except its last element is changed by subtracting g. Right? So u differs from a only in this element. Now because this is a minus sign here and this is a minus sign here, this is really an addition. And u is actually, the length of u is actually longer than the length of a. U is actually longer than a, and that's why we chose this particular sign here. In particular, u can't be 0 unless a is 0. And u won't be any smaller than a. Right? Now, we're going to use a householder transformation based on the vector u, and that's going to do the job of annihilating these elements. We need to know the length of u, and in the Fortran program, that's called h. Some other things are called h too, but it's called h also. That's the length of u squared over 2, and there's a cheap way to compute that. The length of u is obviously closely related to the length of a, and in fact, we don't actually have to find the length of u directly. We can find it from the length of a by subtracting a n comma 4 times g. Right? So this is an identity that you have to verify for yourselves, and this is how the length of u is actually computed. Now, the householder transformation is a random modification of the identity, namely it's I minus 1 over h u transpose. Now, it cannot be emphasized too strongly that this matrix is never formed. Right? We don't have any storage in the memory in the subroutine for P. Instead, we want to form PAP, and let me write that up here, because I want to write it out, formula for it. PAP is I minus 1 over h u transpose times a times I minus 1 over h u transpose. Now, if we were actually to form these matrices and multiply them out, this would be a heck of a lot of computing and would make the process prohibitive. But if we multiply these out on the board instead of in the computer, we find that that's a minus 1 over h u transpose a minus 1 over h u u transpose plus 1 over h squared u transpose a u transpose. And the neat way to write that is a minus u v transpose minus v u transpose, where I guess I just ripped part of this off, where w is 1 over h au and v is w minus u transpose w over 2h times u. Okay. Now, I think Jim worked out this relationship before. The fact that this thing can be written in this form, or if not, you can just verify that this quantity is another way of writing that. Okay? Now this is a much cheaper computation than this. This just says that The new, we just have this Fortran, this statement. The new Aij, let's say Aij prime, is the old Ij minus Ui Vj minus Vi Uj. And that's just a number of operations proportional to n squared. In fact, there's 2 n squared multiplies, but by symmetry we only have to do half of them. So it's like n squared multiplies for this part of the computation. Whereas if we did it this way, it would be lots of n cubes. Okay? So the continuing then with what we're going to see in the program, recall that U is stored in the last row of A. That makes the calculations, the flow of the program a little hard to follow, because you're not sure. You're going to see a whole bunch of A's there, and some of them will actually be the matrix, and some of them will actually be this vector U, because the vector U just differs from the last row of A by 1 element. Okay, then we're going to compute AU in order to get what I call W. Now, that's simply a matrix times a vector. It's very easy to do, except I promised never to touch half the matrix. So I've got the matrix A and the vector U, except the vector U is actually stored in the last row of A. Moreover, I'm not allowed to go near that part of the matrix because the user wasn't provided to put any matrix up, wasn't required to put any matrix up there. So as I try and take this inner product, which would require me to go across here, as soon as I bump into the diagonal, I have to go down. Right? So the inner product is going to go like that, and this is actually stored down here. Other than that, it's perfectly clear what's going on. Right? Then I simply have to scale that vector, which I just computed, by a quantity I'd computed earlier, and that's defined to be W. Then I'm going to compute the inner product of U with W, and that's going to give me my V is W minus that inner product scaled by 2H and then U. So here's an inner product. Here's an inner product, and here's another inner product. Those are the two basic calculations that go into defining the V that I'm going to use in the actual householder transformation. Okay. Now, one more thing that's going to be a little bit confusing when we go to read the program is, in fact, all these computations are going on at the same time. That is, the accumulation of this underproduct is going on in the same loop that this inner product is actually being formed. So each time we compute a component of W, each time we compute a component of this inner product, we divide it by H, and then we multiply it by U again, and so we're accumulating the V at the same time. Okay, with that, oh yes. Now, we go through that n minus 2 times. Let me get rid of this lousy eraser. We go through that n minus 2 times, and we've gotten the matrix to tridiagonal. That would be all the work there is in tread 1. Now, tread 2, in addition, accumulates all those transformations. Now, you could have a second array in which you're accumulating the product of all the p's defined by these u's as we go along. You could have a second array in which that's accumulated. But one of the great advantages of the householder reduction is that that accumulation can actually be done on top of the original matrix. And that little piece of code is one of the trickiest and most ingenious things I've ever seen. And I'll try and give you some idea of what's going on. Right? When we're done with the process I've described so far, we have a as we produce the tridiagonal matrix, the axial elements of the tridiagonal matrix are stored in two auxiliary one-dimensional vectors. But the components of the vectors u, which define the transformation, are left in the array. So let me just write here a bunch of u's. This defines the first transformation we do. This defines the second transformation we do. This defines the third transformation we do. And that's all you need to do in order to get to a tridiagonal form with a 5 by 5 matrix. You actually end up doing n-2 transformations. So there are 3 u's here, this one, and this one. And each of those defines a householder transformation. And now what we want to do is compute the product of those 3 householder transformations. Now that product is going to be a full non-symmetric matrix. And we're going to compute it here in this storage. Now let me give you some idea how that goes. There's something here. I don't know what's there. And the rest of the matrix hasn't been altered. If it were tread 1, the rest of the matrix hadn't been altered. If it's tread 2, the rest of the matrix hasn't been altered yet. Well, we'll see. We're now about to alter it if we decide to, when we decide to accumulate the transformations. We're first of all going to, there are 3 of these, P3, P4, and P5. We want to compute that product. All right, we're actually going to say that there are a full n of these things, but the first 2 of them are the identity. So the first one we find P1, which is really just the identity, and we put a 1 there, and we know that the rest of it is the identity. Then P2, we put a 0 here, and a 0 here, and a 1 there. And we now have P1 times P2, knowing that the rest of it is the identity. Well, it's all the identity. But we're now about to form this product, P1, P2, P3. Now, because of the nature of P3, it's going to, the nature of U, the fact it's only got these 2 components, this product here is going to be the identity in the columns beyond the third. So this product is only going to take up this much space. Well, so we've got the components of U that define P3 sitting here. And so we have to form the product of these 2 matrices times this one. And we can do that and form that product and then store it back in here. Right? So we end up at this point now modifying that top 3 by 3 array. And we now have stored the product of the first 3 transformations. It's, of course, just P3, and now we've actually formed P3. And the rest of the product is the identity, but we haven't set that aside because we don't want to clobber this storage. Now we're ready to multiply P4 times P3. We've got the vector which defines P4 here. That ends up modifying all these elements, and as we do it, we wipe out the information that defines the vector. And then, finally, we take the last householder transformation defined by this U and multiply it into the product we've accumulated so far. That modifies every element in the matrix, including these last, which we now no longer need. And at that point now, we have the product of the householder transformations that was necessary to reduce the original matrix to tridiagonal form. That'll later be used in computing the eigenvectors. Okay, let's turn off the lights and look at the code. Yeah. Let's. I don't want that clear up top, Chuck. It won't. It's not legible on the camera. Let's see, am I in the way with the camera? Yeah, I am. Okay, let me get over on this side. Okay, here's the subroutine thread 2. It has arguments defining the array storage and the order of the matrix. Here's the matrix itself. A, D, and E are two arrays where the tridiagonal form is going to be stored. And then Z is going to be the matrix of eigenvectors. And you can actually call it with A and Z being the same array. So that if you want, you can put the eigenvectors on top of the original matrix. If you don't want, you'll save the original matrix. Because the very first thing we do is take the original matrix and transform it into, put it into Z, and now there isn't going to be another A in the whole code. One of the things about that Fortran requires us to be very careful about is taking care of 1 by 1 and 2 by 2 matrices. So all these subroutines work on 1 by 1 matrices and 2 by 2 matrices, and little statements like this are necessary throughout to ensure that. Now we're going to have a backwards loop. This is because we're starting at the bottom and working up. And this is the way to accomplish a backwards loop. I goes from 2 to n. So I is n plus 2 minus I. It goes from n down to 2. We compute the sum of the absolute values. Let's just consider the first case where I is equal to n. So throughout what I'm going to do here now, I is equal to n. So I is n here, and k goes from 1 to n minus 1. And we compute the sum of the absolute values of the last row. This is going to be the scale factor to avoid overflow. All right? If the last row is in fact 0, then if it's not 0, then we're going to have to do it. If it is 0, then we can skip the transformation because there's nothing to annihilate. All right? We take the last row and divide it by that scale factor and then accumulate the sum of the squares. So h at this point is the scaled length of the last row. Now we pick off n, n minus 1. That, in the example on the board, that was zn4. That's the crucial number that determines the sign of the square root. We take that square root, take the sign of that element, and take the negative of that. And we remember that with the scale factor in EI. So that's going to be the subdiagonal element of the tridiagonal matrix. It's stored in E there. Now, H, I said H at this point is the length of A. I said you can get the length of U from H by a cheap computation, and that's it. H is H minus F times G. So H is now the length of U. In fact, it's the length of U squared over 2. Then this is in a way one of the key statements in the whole program. Z of IL is F minus G. That's the thing which changes the last row. That's a statement which changes the last row of A into the vector U defining the householder transformation. Right? So at this point, the last row of A changed its meaning from an element of data to a vector defining the transformation. Right? Now we're ready to start the actual transformation. I've got to take those two inner products. I set F equal to 0. That's going to be accumulating the second inner product. Now I've got some, let's see. What is that statement doing? Why am I dividing? Oh, let's not go into that. Forget that statement. Okay. That's something I really haven't got into explaining yet. Here is the forming of the inner product AU. Remember, U is stored here. This is U, and it's also U down here. We're going across A, except we have to go across it in 2 pieces in order to just use the lower half of the matrix. So that's forming that right angle inner product. As I do it, I'm also forming the second inner product that's going to end up defining that vector v, and that's what's accumulating in F here. Remember, at one point I had to divide by 2h in order to get the vector v, and there's compute one component of that vector v. Then here is the inner loop. Well, this is where almost all the arithmetic in the program is done. You can tell it's the inner loop because it's indented farther than anything else. And this is the statement which I had on the board. Aij is Aij minus ui vj minus vi uj. Right? But of course, they're stored in different places here. You can see that f is really a component of u because f was taken out of the ith row, and that's u. Here's another component of u. And the e and the g are the components of what I called v on the board. E is also something else, though. E is also going to be is also saving the elements of the tridiagonal matrix. In the beginning part, the end part of E is used as temporary storage for this computation. Okay, now I have to undo some of the scaling. We're not paying much attention to the scaling. Now, that's where tread 1 ends. And tread 2 now has this additional piece of code here, which I say is very tricky to follow, but well worth your while to go through this thing. I starts out at 1. Is d1 equal to 0? Yes, d1 is equal to 0, so I skip this. I go down to 380, and I put a 1 in A11. So that's starting to form the identity matrix. I come back. I look, is d2 equal to 0? Yes, d2 is also equal to 0. The first two transformations, well, the last two, but they're going in the other order, are both the identity. And so I skip down again, and I put 1 in the second element of the diagonal and a pair of zeros in the 1, 2, and 2, 1 positions. Right? Now I come back, I is equal to 3, and I'm really ready to go to work. And this involves, let's see, I is equal to 3, so it involves working with the, oh yes, here's an inner product involving the ith row. So this is taking the u out and forming the inner product necessary to apply the householder transformation. And then this is actually completing the householder transformation, and the piece of storage necessary to define it is no longer used. All right? So on this side of the statement, part of this is some of these z's represent the u's that define the householder transformations up to what point. Other of these z's represent the accumulation of the transformations. Okay, that's a quick look at the code for tread 2. Let's go on back up to the board, turn the lights back on, and talk some about TQL2. When did I start? When should I finish? 20 minutes, okay. I have a philosophical and a pedagogical comment to make about that kind of code. When that code was written in Argonne, there was a great deal of care given to try and save storage. And so the fact that the variables f, g, and h in that last program are all used for 3 or 4 different quantities makes it very difficult to understand and read that by human beings, especially people who aren't familiar with the details of that code. I think I think we're beginning to appreciate the fact that kind of programming is not a good idea. And in order to debug and understand and modify the program, you've got to take into account the fact that human beings are going to read it as well as computers. That's a minor criticism compared with the fact that that programming was really, except for that programming is really very well done. And it's very straightforward for the most part to translate it from Algol to Fortran. Okay, let's talk some about the QR algorithm. And there's a couple of points which I want to discuss. In a way, they're minor parts of the program. We're not going to deal too much with the actual transformation. That's pretty complicated algebraically. But I want to discuss a couple of things: testing for convergence and computing the shift. The test for, so we're talking now about TQL2. Well, these comments apply equally well to TQL1 and TQL2. And the first thing is the test for splitting and convergence. And again, this comes back to the graded matrix business. The matrix looks like, now let's see, I guess I've got D1, E1, E1, D2, E2, E2, D3, E3, let's go down a couple more, E3, D4, and so on. And, well, since we've been working with 5x5 matrices, let's say E4, E4, D5. And then that's the end of my matrix, but I've still got some more room left in E, so I can put a 0 here in E, which is really outside the matrix, and we'll see the meaning of that in a minute. Okay, so that's the data structure for the TQL algorithm. Let me write down a little bit of the code here. B is equal to 0, do 290, L equals 1 to N, H equals machep times abs of D of L plus abs of E of L if B less than H, B equals H, do 110, M equals L to N if abs of E of M is less than B, go to 120. 110, continue. Okay? Now, the loop to 290 is the main loop of the program. L is going to be the index for the eigenvalue we found. And we're first of all starting out trying to find the first eigenvalue. Now we've got to decide when a subdiagonal element is negligible. If E1 is negligible, then D1 is in fact an eigenvalue. Right? So in order to decide what negligible means, we compute this quantity H, which is the machine accuracy parameter, 10 to the minus 16th on the 360 essentially, times, now not the whole matrix, but just the current diagonal and subdiagonal elements. And then we compare that H with what we've been using so far. Of course, on the first step, we haven't been using anything so far. And that's going to be our tolerance. So the tolerance is machine tolerance times a quantity which gets bigger as you go down the matrix. Right? So this has to do with the grading. We present it with the small elements up here and the big elements down here. And that means we have a tighter tolerance, a smaller tolerance up here than we will have when we get down to the end of the matrix. Right? Now, if we presented the matrix the other way around, we would start off with the big element up here. We'd have a big tolerance right from the very beginning, then we get down here to the small stuff, we're going to end up declaring things negligible when perhaps we could do better. And as a result, the eigenvalues would be determined less accurately. But anyway, we start off with the small stuff up here. We're doing the QL algorithm here. Okay, so that's the check for a negligible subdiagonal element. We start here when L is 1, we start looking at the subdiagonal elements until we find one as negligible. Now usually we won't find one as negligible until we get down here. That's why we stuck that 0 in there, because that's certainly negligible. Right? And boy, that's a less than, not a less than or equal to. It's less than or equal to. Woo! That make a big difference, because sometimes you want to, yeah, it has to be that, or else it wouldn't work down there. Okay. So usually at the beginning, if the matrix doesn't split up, that'll be the first negligible element. Maybe an earlier one will be negligible, in which case we can cut the amount of work down. After we've done a couple iterations, this one will be negligible, and we'll be able to accept that as an eigenvalue. Right? Now, let me modify this now to indicate, I think if we were programming this today, how we would get rid of the Macheps. Instead of taking Macheps times these maximum elements, let's just get rid of the Macheps. Right? So B is the sort of the norm of the matrix we've been working with so far. And now we want to decide whether E is negligible compared to B. And in order to do that in a machine-independent way, let me put this in. C, for example, is abs of E of M plus B if C equals B, go to, what was it, 120. Right. Now, 110 is continued. Now, Macheps is gone. I don't need to know the accuracy of the particular machine I'm working on. B is what I want to, B is the norm of the matrix so far. And I add the hopefully small element to it. Now, with the round-off error of the machine, if this thing is really negligible, when you add it to B, it won't change B. And so C will be the same as B. And I can ask here if C is equal to B. And if it is, I'll skip. Right? Now that kind of modification would take TQL2 and make it machine independent. And that's all that's necessary to do. You don't want to actually, you want to use the actual variable C so that rather than put this arithmetic in here for reasons having to do with machines with double-length accumulators and so on. But I recommend that I would recommend that this change be made, except for except then we have to go through the whole testing and certification business over again. Also, on some of the other routines in EISPACK, particularly the bisection routines and the inverse iteration routines, where the tolerance is much trickier than it is here, it's not quite as easy to do this kind of thing. Okay. That's the test for convergence, for splitting and convergence. And they're done at the same place in the code. You then have another test to see which element it was you decided was negligible, to see if it's really a split, if you found an eigenvalue or not. Now we come to the computation of the shift. The shift in the QL algorithm comes out of the upper 2 by 2. And we want to find the eigenvalue of the upper 2 by 2 closest to the upper 1 by 1. Now, the naive approach would be to take this little 2 by 2 eigenvalue problem, lambda squared minus d1 plus d2 lambda plus d1 d2 minus e1 squared is equal to 0, and say that lambda is d1 plus d2 plus or minus the square root of d1 plus d2 squared minus, well, minus d1 d2 plus e1 squared over 2, and then choose plus or minus to get lambda closest to d1. Right? Now, you will find other versions of QR algorithms which do exactly that. Write down this formula or something like that and call that the QR algorithm. Now, that doesn't work. And it doesn't work for a couple of reasons. The simplest is to take a situation like this. Say we had 1, 10 to the minus 5, 10 to the minus 5, 1. If you carry out this computation, you'll get 2 plus 2. Well, let's see, it depends on exactly how it does. The trouble is that in this version of the formula, we have, oh, it's if it gets parenthesized like that. Yeah. If that's how it gets parenthesized, then this thing won't work, because this will be 1 plus 10 to the minus 10th, and the 10 to the minus 10th will be lost, and then we subtract it from 1, and we get a 0 in here. I guess there's got to be a over 2 here. And then we subtract here, and we end up getting a 0 shift, or a shift, D1 is the shift. And the effect of E1 is completely lost. All right? So the actual computation of the eigenvalue of this, let's maybe leave that formula on. The formula that's actually used looks quite a bit different from that. And I can just say that lambda is equal to, and now I'm not going to have time to go through the algebra to derive this, d1 minus e1 divided by d2 minus d1 over 2 e1 plus the square root, sorry about that, plus the square root of d2 minus d1 over 2e1 squared plus 1. Okay. Now, I claim that with a little algebra, you will find that that lambda is equal to that lambda. But from a numerical point of view, this one, well, it's going to be plus or minus there, this one is much more satisfactory than that version. These notions about solving quadratics accurately are beginning to be reasonably well known. Forsyth has written a couple articles about this kind of thing, and here's an instance where that comes up. Now, we want the lambda that's closest to d1. That means we want this correction to d1 as small as possible. That means we want the denominator as large as possible. That means we should choose the sign of the square root to be the same as the sign of the thing in parentheses. So the thing in parentheses occurs twice. We compute that in the program. We square it and add 1. And then whichever sign we have here, we use that same sign in the square root. And that's the way we make sure that the shift is the one we want. Okay, let's take a look at the code for that and point out a couple of those points. So let's turn off the lights again. There. Okay, here's TQL2. The fact that it's 2 means we're going to accumulate the eigenvectors. So the main data is contained in the arrays D and E, which are one-dimensional arrays. Z is just running along for the ride here. And there will also be an error indication, an error indicator which will never be used. Now here we've made chaps equals question mark. That's because we don't know what machine we're running on. First thing we do is shift the E's from where householder put them to where TQL wants them. Then here is the sort of local, what I'd call the local norm, or the norm of the part of the matrix we've looked at so far, really worked at so far. And here's where we check to see if the subdiagonal element is negligible compared with MACHEP times that norm so far. Okay? Then here's where we form the shift. Let's see. If G is D1 and P is D2 minus D1 over 2E1. That's the quantity that was in parentheses on the board. And then I take the square root of 1 plus the square of that and choose the appropriate sign, divide that into EL. And now that is the correction. This quantity on the right here is now the correction to DL. If I subtract that from DL, I'll get the shift. Now, this is the explicit algorithm, so I'm going to subtract that from all the diagonal elements. And I can subtract it from DL in particular just by storing it in DL. This is a change from an earlier version of TQL, where the shift was computed as DL minus that, and then the shift was subtracted again from DL. That's a sort of a minor loss of accuracy that occurred there. I don't know, is that important, Jim? Yeah. It's not very important, but anyway, you can do it this way, and it might give you a slight improvement. Then we do go through, beginning at L plus 1, and subtract the shift from all the rest of the diagonals. Now that can be utter disaster if the matrix is if it's a graded matrix presented in the wrong way. Okay, now we're ready to do the actual guts of the transformation. Luckily, I'm running out of time, so I don't actually have to go through the details of that. There it is. There is quite a bit of algebra that goes into deriving this particular form from, say, the matrix formulation which Wilkinson has been using. The key thing is, let's see, we have to, am I going to be able to write on this kind of thing? Remember, we're going to want to form, no, I can't. Well, okay, maybe I'll go back up to the board and discuss that later. There are sines and cosines which could get computed from the ratios of diagonal to off-diagonal elements. A crucial thing here is how to compute the square root of the sum of squares. In computing the denominator in the sine of cosine, I want, say, the square root of a squared plus b squared, where a and b are two elements. Now, there's a possibility of underflow and overflow at that point. The square root might be well in range, but the square of the square root outside of range. So that's the reason for this little bit of logic here, a kind of pivoting, and so that the square root is always obtained in a way which won't underflow or overflow unnecessarily. Then here's the only difference between TQL1 and TQL2, is here is the application of the Givens transformations to the z's that we went to all the work computing in TRED 2, so we're accumulating more transformations. When we get done, we will have accumulated all the transformations that reduce A to diagonal, and so those will be the eigenvectors. We now know how to do this computation with about half of this much work, and that's going to be a subject of some lectures here tomorrow. The majority of the arithmetic spent in this particular subroutine is spent right here in these 3 or 4 lines. Then at the end, there is a sort to get the eigenvalues and corresponding eigenvectors coming out in monotonic order. We really ought to spend more time looking at this part of the code, but I guess we'll have to leave that for another lecture. Okay, well, we don't have time to really go back up to the board, so let's call that quits then.